We are now going to look at two more options that we have with Riemann sums, which is the midpoint rule and the trapezoid rule. So again, with that left and right hand sum, we were just sort of arbitrarily deciding, okay, we're going to use the left hand point endpoint to find all of our heights, or we're going to use the right endpoint to find all of our heights. Another option is that we could take our interval from A to B that we've divided up into however many pieces. And they should be equal pieces. Let me draw something a little better here. And instead of taking the right or the left hand, is that we could say, okay, let's take the midpoint of each of those intervals and use that midpoint to find the height of our rectangles. So in terms of our notation, when we're doing the midpoint, we do this m sub n. So again, that m tells us it's a midpoint rule. N is our number of intervals, and the length of our interval is delta x. So we talked about this in the previous video that we've got b minus a and b are parts of our interval, our beginning and end of our interval, and n is the number of subintervals that we want to make. And we won't worry too much about this just right now in a minute. In the next video, that will make a little more sense. But another way that we can do a Riemann sum is instead of making rectangles, we could actually make trapezoids. So let's look a quick picture down here. So here's our midpoint picture. So we've got a graph here and we've got an interval. And again, instead of using, this has 4 intervals, either one of the two endpoints, we've decided to use the midpoint to get our height here. So our midpoint, we take that output, and that's going to be our height. And that midpoint, how we get that is it's literally the average of the two of our, I wrote the wrong subscripts on there. It's the average of our two endpoints. So you take x sub 0, 1 sub, or x sub 1, x sub 0, add them together, divide by 2. That gives you the midpoint. Or you can actually just, that's usually pretty easy to figure out. The trapezoid rule is that instead of rectangles, we're going to make trapezoids. So we're going to take the height on the left and the height on the right here and connect those two heights with a line. And we're going to make a trapezoid. And we're going to use that to approximate the area. And we'll talk a little more about the difference kind of between these two methods, but we get kind of an interesting idea right there. So the height of a trapezoid, how you find that, and the way to view this trapezoid that we have is that it's a trapezoid kind of on its side, so that this is one of the bases, base 1, this is another base 2, and this is the height of the trapezoid. So it's literally that we took a trapezoid that would have been sitting like that and turned it 90 degrees onto its side. Because the area of a trapezoid is 1/2, so I can write here 1/2 times base 1 plus base 2 times the height. So in terms of this trapezoid right here, we've got 1/2 times the base 1, which is the height, that f of x sub 0, and then f of x sub 1, it's our other height over here, and then our height is that delta x. So what our trapezoid rule ends up looking like, if we look at this one down here where we've got 4, we've got 1/2 that first trapezoid that we had times our delta x, and then our next trapezoid would be f of x sub 1 plus f of x sub 2 times delta x. So a way to view the area of a trapezoid is that you're taking the average of the bases and then multiplying it by the height. And then 1/2 f of x sub 2, f of x sub 3, delta x, and then one more, I think I'm going to be able to get this on here, x sub 3, f of x sub 4 times delta x. So if you look at the common factors in this summation, we've got 1/2 and delta x in each of them. So we could factor that out in front. I'm going to move this down just a little bit. I'm going to change my color. So we get 1/2 delta x out in front. So notice in our trapezoid rule, that's sitting out in front. And then we have f of x sub 0 plus f of x sub 1 plus another f of x sub 1 plus f of x sub 2 plus another f of x sub 2, f of x sub 3. I'll do a little highlighting here in a second to show you again kind of where all of these are coming from. So this first one, let's change our color here. This first one is right here. This one right there is right there. We'll go kind of alternating colors. There we go. So notice here we have one f of x sub 0, one of them, and one f of x sub 4. Everything else, we have two of them. So notice up here in our trapezoid rule, we've got one of our initial endpoints, one of our final endpoints, and everything else is times 2. So that gives us the area of each of those trapezoids. So that's where the sort of like cryptic looking sum comes from. There's not a nice closed summation form for the trapezoid rule, which makes it a little less advantageous versus our right and left and endpoints. But let's look at an example of doing each of these. So this should be a familiar function, and we want to find the trapezoid and the sum, or the midpoint in the trapezoid for 6 subintervals. So again, what I like to do is draw that number line, figure out my delta x, which we should know what it is. If we watched the previous video, it's the half. And so splitting this up, again, I think I made things too small. There we go. So we're going to look at finding the midpoint right here, which is going to be a 4th. Right here is 0.75. So again, you can take your two endpoints and average them, or oftentimes on ones like this, it's pretty easy to figure out on your own what each of those midpoints are. But those 6 midpoints, those are what we're going to use to find the heights of our rectangles. So our midpoint with 6 subintervals, it's going to be, again, 1/2, that's our delta x, times f of 0.25, f of 0.75. So each of these midpoints plugged into our function. So we need to figure out what each of those y values are. And we're going to get, in this case, oops, I wrote an equal sign there where I shouldn't have. Got a lot of numbers to write down here, so sorry, this is a little bit boring to watch this part of the video. But maybe while I'm doing this, you could be drawing a graph of this in Desmos. But remembering that each of these are giving us the heights of those rectangles. We add them all up, we multiply them by our delta x, and we get 5.875. That's our height there. Our height's all added up, and then we get 2.9375 for our approximate Riemann sum there, or approximate area with that Riemann sum midpoint. So our trapezoid rule, so this one's a little bit tougher. So we've got the 1/2 that again just comes from the area of a trapezoid. So that's that first 1/2. This second 1/2 that I'm going to do, that's our delta x. So that could be a different number. And then we're going to do f of 1, not f of 1, we're going to do f of 0. So our initial endpoint, and then 2 times all of our other endpoints. Sorry, my handwriting is getting a little bad here. So 2 times f of 1, 2 times f of 1.5, 2 times f of 2, 2 times f of 2.5, and then our last endpoint doesn't get multiplied by 2. So again, back up here, that initial endpoint and that ending endpoint, those aren't multiplied by 2, but every other endpoint in between is multiplied by 2. So we're going to get 1/4, and 2 times a 4th, 2 times 0, 2 times a 4th again. Sorry again, super boring to watch me write multiplications down, but I want to make sure that you can go back later and see what we've done. And then that last one's 4, so we get 1/4 times 12.5, and that's 3.125. So on our previous video, we got our left-hand sum with 6 intervals was 2.375. Our right-hand sum was 3.875. So those were our, we've got basically now 4 different approximations to that Riemann sum. The actual integral from 0 to 3 of this function, I won't figure it out right now. There's an algebraic way to do this, but it actually is 3. So they all give sort of okay approximations to this Riemann sum. You know, this guy is off by, it's sort of low by -6.25. The right-hand sum is an overestimate of 0.875. The trapezoid is an overestimate of 1.25. The best one actually is the midpoint, and it's an underestimate, but it is really pretty close. It's only under by 0.0625. So of our 3 or 4 different options, that was actually pretty close with only 3 intervals. And this is kind of something interesting about Riemann sums, that midpoint actually generally is your best approximation with the least amount of rectangles.